Oh.
Okay, so Noppadol, you are ready?
Yes.
Ready to go. Okay, so today we are very happy to have Noppadol Mekareeya from Milan, who will tell us something about Argyros-Douglas theories and marginal deformations and 3D mirror theories. Take it away.
Thank you very much for giving me the opportunity to speak at the QFT and Geometry seminar series. Today I'm talking about Argyros-Douglas theories, some important aspects of these theories, namely the marginal deformations and 3D mirrors theories. So this talk is based on 3 papers appear on arXiv, and in collaboration with Simone Giacomelli, who is a postdoc at Milano Bicocca, Matteo Sacchi, who is now a postdoc in Oxford. Also these 2 papers with Federico Cata, who is a postdoc in Durham, Simone Giacomelli, and Alessandro Minino, who is a postdoc in Desi. So we are talking about an infinite class of n=2 superconformal field theories in 4 dimensions. These are known as Argyros-Douglas theories. The feature of these theories are the presence of the Coulomb branch operator, which have fractional scaling dimension. This make this class of theory distinguished from the usual 4D n=2 superconformal field theories. Some of these theories are known to be identified at singular points of the Coulomb branch of 4D n=2 gauge theory. So you take gauge theory, go to Coulomb branch, and some have some special singular point where the massless dyons are related, which are relative non-local. Basically, they become massless at this point. This makes the theory intrinsically interacting. So Argyros-Douglas theory has a long history. It was first discovered in 1995 in n=2 4D n=2 SU3 super young males. There's this special point that I mentioned. Later, the same theory, the same superconformal field theory was realized in 4D n=2 SU2 gauge theory with one flavor, discovered by this gentleman. Nowadays, this Argyros-Douglas theory is often referred to as the A1, A2 theory in the notation of Chekotny-Naiske-Vafa, or I2, 3 in the notation of CN Zhao. So I will stick to the former notation. I will explain further what is how can you characterize this A1, A2 theory. But let me explain what's the properties of this A1, A2 theory. This theory has one-dimensional Coulomb branch, which we call rank 1. It has a single Coulomb branch operator, has dimension 6/5, and the central charges A, C can be computed to be these numbers. Now, due to the lack of n=2 marginal deformation, because of the dimension 6/5, and this is a single operator we have, this theory does not admit the n=2 Lagrangian description. However, quite nicely and surprisingly, in 2016, it was discovered that there is some 4D n=1 gauge theory. Upon flowing to the infrared, it flows to the A1, A2 theory. And a feature is also that the supersymmetry get enhanced in the infrared. But in this talk, we will not talk about n=1 gauge theory, but we will stick to the n=2 gauge theory and its property. It is common nowadays to refer to any 4D n=2 superconformal field theory with the Coulomb branch operator with fractional dimension and Argyros-Douglas theory. So this term captures any 4D n=2 SCFT with the fractional Coulomb branch dimension. Now, by now, a vast number of such theories are known, and there are basically 2 main constructions. One is to use class S construction, namely you take a 6D2,0 theory compactified on a Riemann surface with punctures. And the other is to use geometric engineering in type 2B via compactification on singular Calabi-Yau 3,4. So, okay. So in this talk, we will focus on some infinite classes of models. These are known as AM, AN, which is isomorphic to AN, AM, or in the notation is IN plus 1, M plus 1. So this is the first class of theory, first discussed by, generally discussed by Cecotti, Naiske, and Vafa, and generalized by Scheer in 2012. The second class of theory that we are discussing is DP-SUN. These are names for the moment. These are discovered by Cecotti del Sotto and Cecotti del Sotto Giacomelli. We will also discuss the closely related theories, namely AM, DN, DMDM, and DP-SO2N, but not in detail. So let me tell you how to characterize these two infinite classes of theories. So they are characterized by Seiberg-Witten curves and the Seiberg-Witten differentials in the standard way. So AN minus 1, AK minus 1 is described by this Seiberg-Witten curve with this Seiberg-Witten differential. Similarly, for DP-SUN, the distinction is look very similar, and this is described by different Seiberg-Witten differential. Since Seiberg differential is related to the BPS mass, it carries scaling dimension 1, mass scaling dimension 1. And by the homogeneity of these equations, we can assign the consistent scaling dimension to the parameter as follows. For example, for x in AN minus 1, K minus 1, you can assign to be K over N plus K, Z to be this one, and the Uij to be this one. Similarly, you can do similar thing for DP-SUN. Okay, and the sum in these are restricted to the terms such that the parameter Uij are greater than or equal to 0. So what are the meaning of this? So Uij such that the scaling dimension are greater than or equal to 0, greater than or equal to 0 are called deformation parameters. These are quite important and play important role in what I'm going to discuss next. So for AN minus 1, AK minus 1, this is the scaling dimension. I just copied from the previous page, basically. And Uij such that Uij is greater than 1. This is called Coulomb branch operators. These are in one-to-one correspondence with the Coulomb branch operators of the theory. And if you count number of them, this is called the rank of the 4D theory. So when I said the rank of the Argyros-Douglas theory, I mean by number of Coulomb branch operators. Sometimes it's called Coulomb branch dimension. Uij such that the dimension, the scaling dimension is 1 corresponds to mass deformations. And basically, if you count the number of possible mass deformations, this corresponds to the rank of the global symmetry of the theory. And suppose you take AN minus 1, AK minus 1, and you count Uij such that this is 1, you will discover there are GCD, K, and N minus 1 number of mass deformations. And DP-SUN, you can do similar thing. It has at least SUN global symmetry. So how do we see that? So you count the set of mass deformations as usual, and you discover that if you look at the curves here, there are 2 sets basically. Number 1 is U0J, where J goes from 0 to N minus 2. This corresponds to the mass Casimir of the SUN global symmetry. So we see SUN global symmetry from here. And there are extra ones, namely the one generically they're given by anything that is not counted here, that the Uij equal to 1. And there are GCD P comma N minus 1 of these extra one. So these give rise to an extra symmetry in addition to SUN. And quite interestingly, many theories admit UIJ such that the scaling dimensions are 0. And these correspond to exactly marginal deformations in the theory. And well, to be strict, I should say 4D n equal to 2 preserving exactly marginal deformations, which we will go into detail later. Okay, so let me give you an example to not make the talk too abstract. Take D2SUN theory. Okay, it turned out that if you take n to be even, this is a Lagrangian theory. If you look at the curve, you look at the differential, you look at the Coulomb branch spectrum, you look at the properties of this theory, it coincides with 4D n equal to 2 SUN gauge theory with 2n flavors. And as I said, the flavor symmetry is at least SU2n, and in this case, it's SU2n times U1. Well, in general, if you take P divides n, dPSUN always admit the 4D n equal to Lagrangian description. However, the case where n is odd is interesting. Here are the scaling dimension of the Coulomb branch operators. And you can see that there's no n equal to 2 marginal deformations here. In this case, when the theory is there are no n equal to 2 marginal deformations, the theory is said to be isolated superconformal field theory, and there's no n equal to 2 Lagrangian description. By the way, this doesn't rule out the possibility of having n equal to 1 Lagrangian that flows to this theory, as I said earlier. Let me note some interesting isomorphism. It turned out that some of these theories turn out to be equal to each other. You look at the curve, you look at the differential, they are the same. They look at the Coulomb branch spectrum. For example, dPSU2 is the same as A1dP. You go to A3G, it corresponds to D3G. dPSO6 is equal to dPSU4. Okay. Another interesting thing is that if you take dPSUN or dPSO2n, this theory can be realized as a class S theory, respectively of class of A type or D type, with the Riemann sphere with an irregular puncture and a regular puncture. And when P is greater than n in the dPSUN or dPSO2n, you can give a vacuum expectation value to close the full puncture totally, and dPSUN become A, A theory, dPSO2n become A, D theory with these parameters. Observe the following. If you want to get A, A theory with arbitrary parameter, you can appropriately tune P and N appropriately, and you can get any of these. Okay, this is quite important, and we will utilize this fact. Okay, so now come to main result number 1, namely n equal to 2 preserving marginal deformations. So we have shown already that some of these theories have n equal to 2 marginal deformations. This correspond to UIJ, such as scaling dimension are 0. It turned out that these number of marginal deformation there are 3 cases, namely n equal to k when k divide n or n divide k and n not equal to k or otherwise. And it depends on the GCD of these quantities. And for dPSUN, it's quite simple. You compute GCD of P and N. If N divides P, become a GCD -2, and N not divide P, become a GCD P and -1. Okay. Now, if there is n equal to 2 preserving marginal deformation, you can go to the cusp, the weakly cusp, why described by the weakly gauging of various isolated SCFT. So you take any Argyres-Douglas theory. Suppose there is some marginal deformation, you can decompose it basically into an isolated theory. For example, isolated 1, isolated 2, up to isolated m+1, and connect them by weakly gauge them by by a certain group, G1, G2, Gm, for example. Let me give you an example. Take D4SU6. Yes, according to this rule, there is, according to this rule, there is one marginal, n equal to 2 marginal deformation, and you can decompose it like this. A3A5, you can decompose it like this. And for example, meaning this notation, meaning that SU3 flavor symmetry of this CFT is weakly gauged with an SU3 subgroup of this theory. So let me be more explicit. How do we see this? So take D4SU6 and decompose into this. And if you study Coulomb branch spectrum, you see the following. So D2SU3, I already described some slides ago in an example of the D2SUN when n is odd. It's an isolated SCFT with this Coulomb branch operator. Okay, so here are the result. And D4SU6, you can see that it has spectrum of D2SU9 with the spectrum of D2SU3 and extra 2 and 3. And this is indeed the Casimir of the mass Casimir of SU3. So this indicates that there is a SU3 gauging. So this is how you can also see. You can also test this, for example, by computing A, C central charges by technique of using this technique of these two papers. You can compute A, C of these theories. And it turned out that it's the A, C of this plus the contribution from the SU3 vector multiplet plus the A and C of this theory. And you can also test in example number 2. A general result, well, assume without loss of generality that the K is greater than N, because this can be interchanged. You can write it in this form where the notation is defined here and the full puncture in this theory is partially close to this. So the gauging is conformal. This part is always isolated and this part has a conformal manifold. Okay, so this you can always decompose it in this form. Now, this is quite interesting that you might ask, okay, now look like A, you can always decompose into DPSU and DPSU. Fine. Is this always the case? The turn out that no, some gauging may not involve AMAN or DPSUN. In fact, as pointed out by the paper by Cyril Crozet, Giacomelli, Sakura, and Wang, it turned out that if you try this for DPSUN, there is some new, I put in the quotation new, because some of this is known, but mostly not, that has some new CFT described by this curve and this differential, gauge with the dp minus q sun minus n, basically. So upon this, go to the weakly coupled cusp and do this some weakly gauge, you can have element of a new theory in this setup, which is quite interesting. And then some may have more than one description. For example, these often appear in D, D. In D, D theory or A, D theory, there always this phenomenon. It doesn't appear in A, as far as I know. In D, D theory, you always have choices of gauging like this. For example, there is a gauging of SO8 type and SO12 type. And here's the general formula for a conformal manifold for D, D theory.
Noppadol? Yes. Do you have a geometric understanding? Why do we have these weakly coupled cusps? Or like class S CH understanding?
So your question boiled down to that, is there n equal to 2 conformal manifold or not, right? Why do we have this thing? Mm-hmm. At the moment, I would say that we deduce it purely from these curves, right? Because we look at these. Okay, and these curves come from geometry because you can describe this as a hypersurface in type 2b, hypersurface singularity in type 2b, and so it in some ways come from geometry, basically, this data.
Mm-hmm. Okay.
Because I get this curve from the geometric engineering, basically from type 2b. These are hypersurface singularity.
Okay, thank you.
So now let me present the second main result, namely dimensional reduction of Argyros-Douglas theories to 3 dimensions. So before I describe the detail, let me provide some motivations why this is interesting. So first of all, we know that we know already by reading the curves that we can read of the rank of the global symmetry of the Argyros-Douglas theory, but we want to determine the exact global symmetry of the theory, basically, not just the rank. So for example, A1, A3 theory has SU2 global symmetry, and it is known also that A1, D4 theory has SU3 global symmetry. Furthermore, we want to understand the structure of the Higgs branch of these Argyros-Douglas theories. For example, I will show also soon that the Higgs branch of A1, A3 theory is identified with C2 mod Z2. And it's also known that the Higgs branch of A1, D4 theory is the closure of the minimal nilpotent orbit of SU3. Namely, this is the moduli space, the centered moduli space of one SU3 instanton. It's quite interesting structure. And also, can we get interesting 3D n equal to 4 superconformal field theory upon dimensional reduction on the circle? Also, whether these theory admit Lagrangian descriptions. Okay, we'll go into detail of this soon. Okay, so the method that we use is to reduce the 4D Argyros-Douglas theory on a circle to 3 dimension. And as you can see, that it's quite convenient to talk about the 3D mirror theory as discussed by Interlitigator and Seiberg from '96. The Coulomb branch of the 3D mirror theory, of course, is identified with the Higgs branch of the 4D theory in question. This is provide a method to study the structure of the Higgs branch of the 4D Argyros-Douglas theory. And the Higgs branch of the 3D mirror is the same as the Coulomb branch of the dimensional reduced theory. In the more contemporary terminology, this 3D mirror is known as magnetic quivers, but I will stick to the terminology of a 3D mirror. And so let me present the main result of our work. So the main result is the following. If you take AMAN, AMDN, DMDN, DPSUN, DPSO2N, and you study 3D mirrors of these, it turned out that all of them have Lagrangian description. It's quite surprising. These usually don't have Lagrangian description, and some of these not even have n equal to 1 Lagrangian description that flows and have a supersymmetry enhancement. But if you reduce it to 3 dimensions, you go to the mirror frame, all of them with generic M, N, P, and N have 3D n equal to 4 gauge theory description, plus a collection of free hypermultiplets. This is also quite surprising because generically these theories come with a free sector and interacting sector. Furthermore, the 3D mirrors of AM, AN theory and AM, ADN theory, all of these are abelian theories. So quite simple. And the quiver description bear the structure of a complete graph. Okay, this is also quite nice. I'll show you a lot of examples later. However, surprisingly, DM, DN, upon do mirror symmetry, it contains a non-abelian USP gauge group with abelian gauge group. So this is quite a new feature of the dm comma dn. So let me, not to be boring, the general prescriptions for constructing mirrors for these theories for general parameters are given in our paper. But in this talk, I will only present some example, just to make the point clear, and you can look it up. And also, I should mention that to find the 3D mirrors of these theory has been a long-standing subject since 2008 by several authors. Basically, they discuss a lot of subclasses of this theory. So this is quite a long-standing subject. And I should remark that for DPSUN and AMAN, the 3D gauge theory obtained from direct dimensional reduction. Direct dimensional reduction meaning before you apply mirror symmetry are also known. So let me start from these result. So for DPSUN, it turned out that the reduction give the 3D n equal to 2 quiver with mixture of U and SU gauge group with a collection of twisted hypermultiplex. Okay. There are also alternative description with the unitary gauge group with high charge, but I'm not gonna use that description for today's talk. So let me give you an example. We have seen this theory, D2SUN, and when n parameter is n is even, is a Lagrangian theory. It's turned out to be super conformal QCD with SUN with 2n flavors. And upon reduction, it's also keep the 3D n equal to 4, SUN gauge group, 2n flavors. What is interesting is when you reduce the isolated theory into this. So as an observation by these authors, that you can embed this into SUN with the SUN gauge, 4D n equal to 2 SUN gauge theory with 2n minus 1 flavors. And this is asymptotically free theory. And one can also show that the embedding is located at the origin of the Coulomb branch of this theory. A nice observation is that once you reduce this, you turn this SUN into UN minus 1, which is a group of the same rank, but now turn into unitary. The UN, yeah, this is as the same rank, and it turned out that the reduction of the theory give rise to unitary, the 3D n equal to 4 theory with unitary gauge group. Okay.
No, Noppadol?
Yeah.
Can you remind us how you make this claim? What is the evidence?
Yes. Okay. This quite long. There is a long chain of argument, which I'm not planning to go into detail at the moment. But if you don't mind, I could go over it in the after. I have a backup slides on this part. But I'm happy to. But let me emphasize: you can also look at the argument in this paper. Okay. So let me use this observation that if you reduce an isolated theory, you get a unitary. This is quite nice observation that if SU group is conformal, you reduce to 3D, you get SU group. If you can embed the isolated theory into SU group, you reduce, you get unitary of the same rank. This is quite a nice observation. And now we can carry on and apply this observation. So you might ask, what is, for example, take the 6SU4 and you reduce to 3 dimension. What is the theory? Okay, let me tell you the answer. The theory is this quiver. So it has U3, U2, SU2 times U1 gauge group with 4 flavor on your U3. Okay, so the way you can do this is to generalize the previous example. Now you can read off from the curve. So let me write down the curve in full detail. This is the curve that you have seen basically for DPSUN and now written in all detail, highlighted with colors. Now we consider the term UKL, Z to the K, X to the L, okay? And it has these scaling dimension, which we have seen. U0L are usual, 02, 01, 00 are the mass Casimirs of SU4. Okay, very good. So this is SU4, and you have to divide into two classes. When 2 over 3k is not an integer, so you see that there are Coulomb branch operator, okay, that give rise to as previously claimed, that these are Coulomb branch operator of the some isolate, look like a some Coulomb branch operator of some isolated theory. And if you have nk of them, this give rise to a UNK factor. Now you can just compute from the curve, and I highlighted in brown. I hope you can see it. There are 3, 2, and 1. And these give rise to U3, U2, and U1 factor. And in order, you see? Okay, so these already tell us that there are U3, U2, and U1 factors upon reduction. Okay, now there is another class of a deformation parameter where 2 over 3k is an integral, and these are correspond to the conformal gauge, basically. So if you look at this thing, UKL, with these are Coulomb branch parameter for the conformal gauge factor, and the one that equal to 1 is a mass term. Here, U30 correspond to the Coulomb branch operator of the conformal SU2 gauge factor, and U31 is the mass term. And this remains SUM upon reduction. As I said before, if it's conformal SU in 4D, it becomes SU in 3D. So here you have SU in 3D, and you read it off in order. So 4, 3, 2, SU2, U1. And here is the equivalent. So next, I will show how to get the mirror from this procedure. So basically, you start from this quiver, you perform this gauging. And now these are 3D n equal to 4. So you just mirror them, basically. So this is known, so you can mirror them using your favorite technique. For example, these admit Hanani-Witten description. So you can just perform Hanani-Witten mirror and then get to this description. You can rewrite in a nicer form like this, and then you glue together. But one has to remind ourselves that these are the gluing of the Coulomb branch symmetry. So you fuse the tail of the quiver together. Okay, this is the SU2, the part that carry SU2 Coulomb branch symmetry. Once you fuse this thing together, you get this quiver. So this is how the structure of a complete graph arises. So let me tell you what this double line means. Okay, this is quite important. So the notation 1, 2, 3, 2, 1 here, meaning that this theory has U1, U2, U3, U2, U1 gauge group, okay, with bifundamental and with fundamental method as usual. Once you, the way to rewrite it is that I rewrite the single line as double line. Double line means that it has two copies of the hypermultiplex transforming under U1 and U1 basically. Similarly here, and once you fuse, you get this thing. And this, you can get the structure of the complete graph attached with the tail. Okay, so this is what I mean by structure of the complete graph, and this is roughly how they arise. Okay, so let's proceed further. So now this is the 3D mirror of the 6SU4.
Noppadol, sorry, can you go to the previous slide? So what exactly the colors mean? The red?
I just say that you glue this part together. So okay, if you look at the symmetry here, this is the part that carry SU2 Coulomb branch, right? Symmetry, and you glue them. This is basically. So you do the mirror side of this basically.
Okay, I see. Thank you.
Thank you. So now from this, as you remember, given dpsun with p greater than n, you can always close the puncture to ap minus n minus 1, an minus 1 theory. And this allows us to land on this by starting with this. So what do you mean by closing puncture in terms of 3D mirror? You just remove the tail because the puncture was, the symmetry of the full puncture in 4D were carried now by Coulomb branch symmetry associated with the tail. So you just remove the tail. So here, you remove the tail 1, 2, 3, you get 1, 1 with 2 lines. You can also read this as U1 with 2 flavors. So the 3D mirror of A1A3 theory is U1 with 2 flavor. And as I promised, this has Higgs branch and Coulomb branch being C2 mod C2. So this confirms also that the Higgs branch of A1, A3 theory is C2 mod C2, and it has the S22 global symmetry. Okay. So we can also repeat this procedure to other theories and find something also quite interesting. For example, D7SU4. If you perform the similar technique of curves and deformation and read off the quiver from the procedure that I described, you would get this one. And you observe that there are some structure here. There's U1 attached to U1, U2 attached to U2. And by the duality that we know from Guy-Otto-Witten, that is UN with 2n minus 1 flavor is dual to UN minus 1, 2n minus 1 flavor with 1 twisted hypermultiplet, you can dualize this quiver into this quiver and get 3 twisted hypermultiplet. So if you know, this is known as the Lagrangian description that describes so-called Tsu4 theory of Guy-Otto-Witten. And you have 3 twisted hyper. And if you mirror, this is self-mirror, and twisted hypers become free hypers. So you have TSU4 and the free hypers. And upon closing full puncture, which you can do because P is always greater than N, you get A2, A3, and you remove this tail. So the 3D mirrors of A2, A3 is the theory of three free hypermultiplets. This is quite surprising that in 4 dimensions, this is an strongly interacting theory. You reduce to 3 dimensions, it becomes free theory. So what's going on? This is quite an interesting physics behind it, actually. But before getting into that, let me also present some more example. And here you see fully the structure of complete graph. So you see that the DPSUN with GCDPN equal to 4 is described by the quiver tail, go down to n minus 1. And then you have to define the sub GCD and dividing this number. And here are the multiplicity of the edges, okay? And these are the number of free hypers. And upon decoupling the tail, you get this thing. So, and this is the prescription. I will not read it through. It's just the reading of this. This example is already clear enough that you can generalize it to any DPSUN and AMAN. What I want to emphasize is that any AMAN theory is just described by a abelian theory with a complete graph structure and a collection of free hypermultiplets. That's it. Now come to a more complicated theory, namely DPSO2N and AMDN. I'm not meant to go into detail, but I would like to point out some structure that's quite interesting. This quiver has an overall U1 that decouple. You can choose it to decouple at some node and open this quiver up, but it's nicer to keep it this way, I think. And observe that the multiplicity is really uniform inside the graph and inside the connection between the graph and the tail. DPSO2N, on the other hand, the quiver was described by tail, but now it's tail of alternating SO USP. This is totally new, according to the best of my knowledge. So you have this connecting with a complete graph. Still, the part in the complete graph is still abelian. Now it has hypermultiplet with charge 2. And if you look at this thing, it has a non-uniform connection And half of the complete graph has one multiplicity, the other half had the other multiplicity. So this is quite an important feature. And the quiver also have an overall Z2 that you have to mod out to get the expected answer that match the global symmetry. You can check this by computing, say, the index or Hilbert series or a lot of quantity that it has a sensible global symmetry. And upon decoupling the tail, you get this complete graph. Okay. So another feature I would like to emphasize for dn, dm theory is the following. As I pointed out earlier in the introductory slides, that it has the abelian non-abelian USP type node surrounded by abelian groups. Okay, so these are example. These are the example of 6 mass deformation, and these are example of 5 mass deformation. This has an overall Z2 that you have to quotient out. This doesn't have one. Okay, so what is interesting about this theory is just another example? I don't think so. So as we know, a D1 or that isomorphic to U1 has a U1 topological symmetry. Okay. In 3 dimensions, upon mirror symmetry, this corresponds to 4D global symmetry. Okay. Or if you like, these are Fourier-Iliopoulous parameter that map to the mass parameter in the original theory and also descend from the mass parameter in the 4D theory. However, since this theory has a USP node, but it's a special USP, it's a USP which is balanced, meaning that it has USP 2n with 2n plus 1 flavor. This has hidden Fourier-Iliopoulous parameter. It's not apparent in the Lagrangian. Even you compute in the index, you cannot turn it on explicitly. And if you count this, it matches with the number of mass parameter in original 4D theory. So let me try. For example, here, 1, 2, 3, 4, 5, D1, plus the central USP, you get 6 as expected. On this example, 1, 2, 3, 4, plus 1, you get 5 mass parameter. Okay. So this is the example of the 3D reduction and 3D mirrors. Any question? If not, let me present the main result number 3, namely the 4-dimensional origin of 3D free hypermultiplex. So we have seen already a large class of Algeria-Douglas theory. Once you upon the reduction to 3 dimensions, this gives rise to twisted hypermultiplet or 3D mirror dual to free hypers. So a curious thing is that what is the origin of this free hypermultiplets from the 4D perspective? It turned out that this quite have a rich physics in the sense that the following. So our claim is the following. If you go at a generic point on the Higgs branch, the theory reduces to a collection of hypermultiplet along with the, so it's not that the theory, you can completely Higgs the theory into a collection of hypermultiplet. There is something that also remains on the Higgs branch, which is a CFT with no Higgs branch. We call it non-Higgsable superconformal field theory. Okay. And the second claim is that if you reduce this non-Higgsable SCFT to 3D, these with rank R become twisted hypermultiplets. Okay. So what is the definition of a non-Higgsable superconformal field theory? We define it, the working definition that we use is the following. It's the 4D n equal to 2 superconformal field theory with no Higgs branch. But there is a non-trivial Coulomb branch, namely rank R greater than 1. Example of this is AM minus 1, AN minus 1 when GCD of MN equal to 1. Okay. So we claim that this theory, upon reduction to 3D, give rise to a collection of hypermultiplets. So what's the argument that you believe that this is correct? So we reduce this theory to 3D, apply mirror symmetry. So mirror symmetry exchange Higgs branch and Coulomb branch. So instead of Coulomb branch, you get a theory with R quaternionic Higgs branch dimension. But since these have no Higgs branch, it becomes no Coulomb branch, or theory with rank 0. Okay. And so far, we know that there is no interacting rank 0 with 8 supercharges and non-trivial Higgs branch. So the above theory must be R-free hypermultiplets. And this justify the point 2 of the claim. Okay, so this rely on this assumption. So let me make an important claim here that this has the, yes.
You also assume that there is a mirror duality, right?
Yes, but it's a mirror in the sense that, yeah, you can, it's still a CFT. I didn't assume that it has a description or anything like that.
Oh, okay, but the argument goes to a CFT with no Coulomb range. So you assume that you have a physical mirrors in theory.
Yeah.
It does not exist.
Right. So yeah. So yeah, it turned out that we conclude that it's a free hypers. So yeah, okay, but it's true that I assume that mirror symmetry can be applied. Okay. But yeah, this is the argument that that if you reduce this type of theory. So let me give you example. These are, for example, of the list of the non-Higgsable superconformal field theory. And if you reduce this, for example, this has rank, let's look at the 3/7, let's look at the A2, A3, for example. We have seen this in some slides before, that it has rank 3. If you reduce it, you have 3 twisted hypers, and if you mirror it, becomes 3 hypers. Okay, this is the claim. And what is another feature of this thing? If you look at 24C minus A, this is a usually this is taken as the quaternionic Higgs branch dimension. The argument is the following: for a 4D n equal to SCFT, whose generic point of the Higgs branch consists of only of collection of H hypermultiplet, meaning you can completely Higgs the theory to H hypermultiplet. Then you can use top anomaly matching between the CFT point and the generic point on the Higgs branch to show that this is true. However, you can see from this list that 24C minus A is either fractional or 0. It's quite interesting. So basically, this is also tell us that, I mean, this should not be interpreted as a dimension of the Higgs branch, and basically it cannot be Higgs to an completely Higgs to a H hypermultiplet, basically. So this is another thing that lead us to study this type of theory and conclude that if you reduce to 3 dimension and you have free sector, the origin of those free sectors are these guys. Okay, so a general statement for AN minus 1, KN minus 1 is that you can Higgs the theory to M minus 1 hypermultiplet, where M is the GCD, and a collection of non-Higgsable conformal field theory. And this, we can specify what are these. So what is the test? The test is that you can match, for example, 24C minus A on both sides and expected they're equal as expected from the Higgs branch flow. So if you give me generic AN minus 1, AK minus 1, I can give you the general structure of the Higgs branch, basically, and I can tell you that there is M minus 1 hypers together with the M copies of this non-Higgsable superconformal field theory. For AMDN, D, D, DPSON is a bit more complicated, and I give you example here. I'm not going to discuss this in detail, but it can be, many of them can be identified. Okay, so this is basically the structure of the Higgs branch and the origin of the free hypermultiplet that I described. And finally, this is in the last 10 minutes, I would like to describe the duality between 3D n equal to 4 gauge theories. So you can consider the theory which are isomorphic to each other. For example, these two. So D3 is isomorphic to A3 as an algebra. So we expect something to happen here. And indeed, as you can see that these two belong to different classes, but they are actually the same theory. These belong to D, D theory, and this belong to A, D theory. And it turned out that they have different mirror description. Let me describe to you how they look like. So we found even 3 duality frames for this thing. So first duality frame has USP2, SO2, together with N flavor, and SO4 flavor symmetry here. Okay. Second theory has SO2, SO2, with 2 copies of half hypers in the two semicolon 2 of the SO2. And this notation, as I said, it means the hypermultiplet of charge 2. And this theory has an overall Z2 quotient. The third duality frame has 3 U1 gauge group with a multiplicity 2, 2, 2n with an overall U1 that decouple. Okay. So I should emphasize a little bit about this notation. When I said M half hypers in 2, 2, it gives rise to SUM square flavor symmetry. The way to see SUM square times U1 flavor symmetry is that you should view these SO2 as U1, and they transform as the diagonal combination and anti-diagonal combination of these basically. And then you see M times SUM times U1, okay? So if you map, so, okay, first of all, the feature of this duality is that it's a duality between orthosymplectic quiver. This one is, you can interpret as abelian. Okay, so it's, you can call it U1 SO2, and this one is a unitary gauge group, abelian unitary gauge group. So this is orthosymplectic with USP, which is non-abelian, and these two are abelian theory. So let's match the Coulomb branch symmetry of each theory. So the Coulomb branch symmetry of each theory is U1 square. This comes from topological symmetry in the frame number 2 and frame number 3. Note that frame number 3 has an overall U1 that decouple because all nodes are gauge. So there are, in fact, 2 U1 square. In theory 1, as I mentioned before, there is one topological symmetry here, and there's a one hidden topological symmetry here, but C1 is balanced, meaning that it has 3 flavors charged under it. So there is an enhancement of this U1, emergent U1. So in total, you have U1 square, which match the 4-dimensional symmetry. Since we claim that these are dual to each other, we should match also the Higgs branch symmetry. So the Higgs branch symmetry is clear in the frame number 2 and frame number 3. Okay, so it has U2n times SO4. So you can see U2n from here, SO4 coming from here, SO4 coming from here, U2n coming from here. With one, you have to look at the operator a little bit. But since it's Higgs branch symmetry, it's not emergent or anything like that. It just you have to look at the right. So you see SO4 factor from here. Here, because it's SO2, you have epsilon tensor and delta. So you can form symmetric square and wedge square of the USP2, and this corresponds to the U2n flavor symmetry current. You can test this by computing further by doing matching the Higgs branch, Coulomb branch dimension, Hilbert series, and indices. Again, there are also 3 duality frames arising from D3D3, A3D3, and A3D3. Okay, so these are D3 theory. And each theory, it turned out to be self-mirror. So if you do mirror symmetry of each theory, it turned out that they map to itself, but these are dual to each other. So we find duality frame for self-mirror theory, for example. And theory number one is actually come from the mirror theory of class S. It turned out to be classes of twisted A2 type. Okay, so this realized that D3, D3 theory. Finally, this thing is also quite interesting. It's D3 with the D4M plus 3 with A3, D4M plus 3. Again, it's the orthosymplectic in this frame. This is always abelian with the Z2 overall Z2 quotient, but they're dual to each other. And you can match again the Coulomb branch symmetry, Higgs branch symmetry, and other quantities. So, okay, since time is up, so let me conclude. So we discussed, I hope, interesting aspects of Argyros-Douglas theories, namely n equal to 2 marginal deformations, weak coupling cups, how to decompose them into several isolated theory connecting with the weak leakage group, reduction to 3D and 3D mirrors, non-Higgsable SCFT on the Higgs branch, duality between 3D and equal to 4 gauge theories, coming from a reduction of different theory that are equivalent but belong to different classes. So there are some open questions. So first of all, are there other dual description of 3D reduction of these theories? Are there simpler, even description that we can make a uniform extension to all of them? What about the class when so far we studied classical algebra. What about exceptional one? And what is the connection with the 4D n equal to 1 Lagrangians? So thank you very much.
Thank you very much, Noppadol, for the nice talk. So any questions? Craig, go ahead.
Hi, Noppadol. That was a nice talk.
Hi.
So I just wanted to ask, so you have these non-Higgsable SCFTs, the Argyros-Douglas type.
Yes.
Are these related to like the 60 SCFTs, which also have no Higgs branch? Do you know?
This is an interesting question. At the moment, I don't know the answer for this, where the 6D origin would be quite interesting to find a connection. I agree. Yeah, at the moment, I don't know.
So there are infinitely many of these non-Higgsable 4D SCFTs.
Exactly. For example, AM minus 1, AN minus 1 with GCD MN equal to 1. All of these things are non-Higgsable. There are, related to your work, there is also the one with A equal to C. Yeah, right. So if you check the table of our appendix, there are a list of them, and there are many that have. It's truly these. So these theory are truly n equal to 2, as you know. This A2 we discussed about this. So these are truly n equal to 2. Doesn't enhance to n equal to 3 or 4, because it has fractional dimension of Coulomb branch.
I see. Very good. Very good. Okay. Yeah. Thank you.
Thank you.
Do you know of a Lagrangian theory which is non-Higgsable?
Lagrangian theory which is non-Higgsable. So there are similar things. Thank you for your question. Yes. So let me explain this to you. This is we are very familiar with this type of thing. So if you take, for example, in some gauge group, let's say SU3, but few flavor, we know that you cannot fully Higgs the gauge symmetry along the Higgs branch, right? There is a vector multiplex that's remain on the Higgs branch. For example, this happens.
You are talking about non-conformal theory.
Okay, I guess. Okay, let's take the better one. Class S with loop. Class S with genus.
Okay.
Yeah, this is conformal. But the notion of the Higgs branch, or the what I call hypermultiplet moduli space, or Hubble branch, or this kind of thing, there is a remaining vector multiplet at a generic point. Right? This is a generalization of that concept.
So, but according to your logic, would those theories reduce to free hypermultiplets?
I'm not claiming that. Let me see. So you said that along these, you have, well, if you take vector multiplet, you reduce 4D vector multiplet, you get 3D vector multiplet, you mirror, you get hypermultiplet. So yes.
So class S theories,
no, you have to look at the part which is along at the generic point on the Higgs branch, right? There is a free hypermultiplet living there in this theory that we are talking about. Free hypermultiplet reduce, it's free hypermultiplet, you apply mirror symmetry, it's become free vector multiplet, you reduce, become vector multiplet, and you apply mirror symmetry, become free hypers, right? So yeah, it's follow in this logic. This is a generalize of that. Yeah.
Any more questions? So let me ask another one, follow up on the question I asked in the beginning about the conformal manifold.
Yeah.
So you have these Argyres-Douglas theories, which have one irregular and one regular puncture.
Yeah.
Right. And then they have these conformal manifolds that you can write as Higgsing of as gauging of two isolated theories. So these isolated theories also have one irregular and one regular puncture.
So, okay. Let me separate your question into two parts. For example, okay. So probably it's best to use example to clarify to answer your question. So in this particular theory, let me, well, generic. Okay, so A3, A5, for example, this has single irregular puncture. Doesn't have a full puncture or anything like that, but you still can decompose it. And each of these theory, so this theory has irregular puncture and has regular puncture, and you gauge the SU2 part of the regular puncture. Okay, here, similar. It has irregular puncture, a regular puncture, and regular puncture carry SU3, and you gauge SU2 subgroup of that SU3.
So can you think about the conformal manifold as moving on the surface, these punctures in the language on the right?
In the language on the right, yes, I think so.
So the conformal manifold here is one-dimensional?
This theory is one-dimensional, yes.
Okay. Okay, thank you. Any more questions? If not, let us thank Noppadol again.
Thank you very much again.
Let me switch off the recording and